Okay, as we continue our discussion regarding probability and probability distributions, an important area to take a look at is something called conditional probability. This is a bit of an extension of our discussion of combinations of events. We talked about the union and the intersection. Well, now we'll spend some time looking at conditional probability. And the expression for conditional probability is really captured as the following. What we're saying is the probability of event A happening given that B it has already happened, or we can take it as a given. That's on the left-hand side of the equation, is equal to the probability of being in the intersection of A and B divided by the probability of B. And okay, that sounds like a lot of jargon, but let's take a look at what it means. And here's the new term we're introducing on the left side of this expression. It's the probability of A given B. That's how we say that, where we've got that vertical line in between A and B. We saw the U for union, the upside down U for intersection. Here we're introducing a new symbol, that vertical line between the A and B, and we express that as the probability of A given B, meaning that we know B is going to happen. Well, how does that relate to what's on the right side of the equation? If you look at the diagram down below, remember we were saying, okay, our universal set is everything in the rectangle. The set A, the circle A, represents the event A happening. The set B is represented by that circle, by the pink circle B. And just to go back to our example, we said, okay, A represents people who are Coca-Cola drinkers. If you're outside of the blue circle, you're not a Coca-Cola drinker. In the pink circle, event B means you're female. If you're outside of the pink circle, it means you're not female. And in this case, A and B intersect. And that dark area in the middle where the two circles overlap, that's the intersection. Those are people who are both Coca-Cola drinkers and female. So here's what's going on. We're looking here now not just at the probability of A, which would be the proportion, if you will, of the people in the circle A divided by the rectangle, the universal set. But in this case now we're saying, what's the probability of A given that B definitely has occurred or is going to occur? In this case now we're not really thinking of the whole rectangle as our universal set. If we say given B, that means, hey, we know we're in that pink circle labeled B. So if we're in that circle, if we're in that set, if we know that the person is female, then what's the probability of them being also a Coca-Cola drinker? What's the probability of A being a Coca-Cola drinker if we know that the person is female? That's what we're saying. And if you think about it from the standpoint of the diagram, it means what's the probability of being in that intersection, being female but also being a Coca-Cola drinker, divided by now not the universal set, but only the circle B. And that's what's represented on the right-hand side of the equation. So this is what we visually are thinking of when we say the conditional probability of A given B is just the probability of being here in the intersection, the overlap area, divided by now the group that we're interested in, which is set B or event B, in this case being female. Okay, so what does that mean? How do we use it? What that leads to is something called the multiplication rule. Let me step back for a second. If you look at the expression here, we say that the probability of A given B is equal to the probability of being in the intersection divided by the probability of B. Well, if we multiply both sides by the denominator on the right-hand side, we end up with this expression. The probability of A given B multiplied by the probability of B is equal to the probability of being in that intersection. And hold this expression in your heads for a while. We're going to come back and see how that reduces to something that we're probably intuitively familiar with, but only in certain cases. Let's talk now about this idea of independence of two events, probabilistic independence of event A and event B. We say that the two events are independent of each other if the probability of A remains the same regardless of what I know about B. So if the probability of A happening is a certain value. And if I say, what's the probability of A given B? Well, if that probability of A doesn't change if I know B has happened versus if B doesn't happen, or if I don't know anything about B, then the two are independent of each other. And we can express that as the top expression here. So if the probability of A given B is equal to the probability of A regardless of B, then the two events are independent. And similarly, if the probability of B given A is equal to the probability of B, once again, the events are independent. So the idea is, does it matter if I know something about B in terms of what my probability of A is going to be? And if it doesn't matter, then the events are independent. If it does matter, if the left side and the right side of either of these expressions are not equal, then there is some dependence going on. Then the fact that I know a person is female does impact the probability of them being a Coca-Cola drinker. That implies there's some dependence of cola preference on gender. And that's the example that we're going to look at in a little bit more detail here. So if you imagine a large city and a random sample taken from the city's population, and in this sample we've observed two variables. We're going to inquire about gender, and we're going to inquire about their preference now of one or the other of two very popular brands of cola. So let's say you're either a Coca-Cola drinker or a Pepsi drinker. And let's say you're either male or female. And we take this data from a large sample, large random sample, presumably representative of the city's population, and we start to capture some information based on the relative frequencies, the relative proportions of things, and we start to populate now a table. And if you look at this, it might look like the output from a pivot table. What we're doing is we're counting the number of people who are male and Coca-Cola drinkers, female and Coca-Cola drinkers, male and Pepsi drinkers, female and Pepsi drinkers, and we're effectively dividing by the overall sample size. And that's going to lead us to our crosstabs or a probability table. And very often in the margins, we'll get what are called marginal probabilities. So if you notice, if we sum across a row of Coca-Cola, we get the probability of a randomly selected person being a Coca-Cola drinker is 0.7 versus 0.3 probability for being a Pepsi drinker. And we can sum down the columns and get probability of being male is 0.4, probability of being female is 0.6. So if this was a large enough sample representative of the city's population, we can find these probabilities of a randomly selected person meeting each of these criteria. And as a good check, the total probability across all four of these boxes should sum to 1. And we see that in this case. The sum of the four boxes equals 1. The sum of the marginal probabilities for the rows equals 1, and the marginal probabilities for the columns, those should all sum to 1. So let's ask our question about the probability of being a Pepsi drinker. In this case, we can just read it off the chart and say, what's the probability of being a Pepsi drinker? Well, it's going to be a probability of 0.3. But suppose we want to know about the probability of being a Pepsi drinker given that a person is female. Well, that'll be the probability now of being Pepsi drinker if we know that you're in this column called female. So now rather than looking at our entire set, we're just interested in the proportion of the population or of the sample that is female. And now we're going to say, hey, what's the probability of being a Pepsi drinker if I'm in this column? Well, it'll be the probability of being in the intersection, being both a Pepsi drinker and female, divided by the probability of being female. So we get a 0.2 divided by a 0.6 for a conditional probability of 0.333, which is not equal to 0.300. So it seems as though in this city, again, if the sample can be assumed to be representative, there's a slightly higher probability of being a Pepsi drinker if the person is female than in the overall population. So there seems to be some probabilistic dependence between the two variables color preference, and gender. And I'll contrast that with a different city. Similar type of survey that's done, and we're capturing probability information, and if these are going to sum to 1, then our remaining value has to be 0.3. And we can add our marginal probabilities and our total probability of 1. And now we can ask and answer the same question. What's the probability of being a Pepsi drinker? Well, we can read across the Pepsi row and see that that probability is 0.5. What's the probability of being a Pepsi drinker, however, if the person is female? Now we're only interested in the female column. So out of that female column, the Pepsi drinkers will lie in the intersection. So it's going to be the female Pepsi drinkers will have a probability of 0.3 divided by the overall probability of being female, which is 0.6. And that gives us a conditional probability of 0.5. And in both of these cases, it'll be exactly equal to 0.5. So therefore, in this particular sample, we would say that color preference and gender seem to be probabilistically independent of each other. So just two examples from a similar survey done in two different cities, showing in one case there's evidence of dependence between gender and color preference, whereas in the other city there's not. And if you think about what the reasons might be, well, clearly in one or the other city, something is happening, particularly in the first city, something is happening that's impacting the color preference of one gender relative to the other gender. And this kind of study is done actually very often in marketing and advertising, where a company, let's say, let me go back actually to the previous city, where it seemed as though there was some dependence here. And I think I said there was a slightly higher probability of being a Pepsi drinker among females than in the overall population. And it could be that Pepsi is doing some test marketing of a new ad campaign that's targeting female cola drinkers. And this is one of the things that companies will do to test to see whether their advertising campaigns are being successful. Are they having the impact that they want? If they'd like to improve their what would you call it, drinkership among females, maybe they go out and they have new billboards in the city with women, chic-looking women drinking Pepsi or something like that. But something seems to be happening in this market that is causing the likelihood of a person being a Pepsi drinker to be increased among the female population versus in the other city. And again, very common type of study done for people who are in marketing and advertising, where they'll test market an ad campaign versus some control group and look to see, hey, are we having an impact? We've run this campaign for a month. Does it look like we're seeing some dependence here, some shift? So again, this idea of conditional probability is one that's quite practical and again fairly widely used in certain arenas. So I want to just close with this idea of probabilistic independence. Remember, we said if two events A and B are probabilistically independent, then the probability of A given B was exactly equal to the probability of A. And if we go back to our multiplication rule from a few slides back, that first term was probability of A given B multiplied by probability of B is equal to the probability of being in the intersection of A and B. In this case now, if the events are independent, that first term reduces just to the probability of A. And then we get this reduced multiplication rule that says the probability of A multiplied by the probability of B is equal to the probability of being in the intersection of A and B. And this is something that we intuitively think about if we were trying to calculate the probability of being in some intersection. For example, again, to go back to cards, if you have a regular deck of cards, the probability of getting a king is 1 in 13. There are 13 ranks in a deck of cards from 2 all the way up to ace. And therefore, the probability of getting a king at random from a complete deck of cards is 1 out of 13. Separate and independent from that, if we were just drawing another card out of this deck, putting back in that king and shuffling the deck, the probability that this time we draw hearts is going to be 1 out of 4, because there are 4 suits, each of which have the same number of cards in them, right? We've got hearts, diamonds, clubs, and spades. So the probability of drawing a card that's in the suit hearts is going to be 1 out of 4. So we put back that card and shuffle the deck again. And now we ask the question, what's the probability that if I draw a card at random, I'm going to draw the king of hearts? Well, we intuitively and practically know what the answer is, but that king of hearts will be the intersection of those 2 separate and independent events, as it turns out, drawing a king and drawing hearts. So the probability of drawing the king of hearts would be 1 out of 13, the probability of drawing a king, multiplied by 1 out of 4. So we get 1 out of 52. And this intuitively makes sense, of course, because there's 1 king of hearts in a deck of cards. So, and we use this intuitively, again, just to think about, well, if I know the probability of being in A, I know the probability of being in B, then the probability of being in the intersection is, well, 1 times the other. But the point I want you to recognize here is that only holds in the case when A and B are independent of each other. That's the only time where the multiplication rule reduces to this form that we're somewhat intuitively familiar with. All right, well, that wraps up this brief discussion on conditional probability, and we'll continue by talking about discrete probability distributions.